Inferential statistics. With inferential statistics, we generally take a sample, or a small subset of a larger set of data, and we use this sample to draw inferences about the population as a whole. Let's consider some examples. You have been hired by the National Election Commission to examine how the American people feel about the fairness of the voting procedures in the United States. How will you do it? Who will you ask? It would be virtually impossible to ask every single American how he or she feels about the fairness of the voting procedures. Rather than asking every American, you should sample the population and then draw inferences about the entire population based on the sample. A sample is a smaller subset of the population. In taking a sample, consider how important it is for us to get an unbiased sample. For instance, what happens if all your sample happens to be composed of Florida residents? Alternatively, what happens if the sample you choose is composed only of Republicans? Since inferential statistics are based on the assumptions that sampling is random, your sample would not provide a valid basis for generalizing the population. As you might imagine, it is very easy for a sample to be biased. Thus, there are strategies that researchers adopt in an attempt to eliminate or decrease the bias in the sample. One of these strategies is the use of simple random sampling. Simple random sampling occurs when every member of the population has an equal chance of being selected into the sample. In addition, the selection of one member is independent from the selection of the other member. In theory, then, the strategy of simple random sampling involves selection into a sample by pure chance. To see why random sampling is important, consider the following ways that a sample can be obtained. To build on your understanding of sample and population, identify both of these and then consider the problems with how the sample was selected. In this example, a substitute teacher wants to know how students in the class did on their last test. She asks only the 10 students sitting in the front of the row to report how they did and concludes that the class did extremely well. What is the sample? What is the population? Can you identify any problems with choosing the sample and the way that the teacher did? The sample is the 10 students sitting in the front row. The population is all students in the class. The problem with choosing this sample is that it is biased. Those who sit in the front of the row tend to be more interested in the class and tend to perform higher in the class than the students who sit in the other places in the classroom. Thus, the sample may be performing much better than the population. If the substitute teacher puts every student's name in a hat and randomly chooses 10 names out of the hat, the sample would not be biased. Consider another example. In this example, a coach is interested in seeing how many cartwheels an average college freshman at his university can do. The coach chooses 8 volunteers, all of whom happen to be women, and concludes that college freshmen can do an average of 16 cartwheels in a row without stopping. What is the sample? What is the population? Can you identify any problems with choosing the sample the way the coach did? The sample includes the female students who volunteer to do cartwheels. The population includes all freshmen at the university where the study was conducted. The problem with choosing this sample is that, again, random sampling is not used, and so generalizations back to the population can be grossly inaccurate. Rather than randomly sample from all college freshmen and ask them to turn cartwheels, the coach chooses only women and chooses only those who volunteered. First, we might assume that women generally outperform men in turning cartwheels. More women are in gymnastics. Cartwheels tend to be an activity that little girls pursue more than boys. And so the number 16 would be biased. Second, those that volunteer to do cartwheels can probably do cartwheels very well. In other words, a person who can't do cartwheels probably would not volunteer to do them. Thus, the sample may be missing individuals who suffer in cartwheel abilities, and hence, the sample inflates the number of relatives in the population. Sometimes it is simply not possible or feasible to take a simple random sampling. For instance, consider that both Dallas and Houston were vying to be hosts of the 2012 Olympics, and assume you are hired as assesses whether Texas people as a whole would prefer the Olympics to the people in Dallas or Houston. Because you have already learned the difficulty of getting every single Texas people's opinions, you know you must get a sample and you want to use a simple random sampling. However, even this may be very difficult. For instance, how will you get a hold of those individuals who don't vote, who don't have phones, and whose addresses have changed? What do you do with those individuals in the sample who happen to move to Texas to California? What do you do about the fact that since the beginning of the study, an additional 4,212 people moved to the states of Texas? As you can see, it is sometimes very difficult to develop a truly random procedure. Recall that the definition of a random sample is a sample in which every member of the population has an equal chance of being selected. This means that the sampling procedure, rather than the results of the sampling procedure, defines what it means for a sample to be random. Random samples, especially if the sample size is small, are not necessarily even roughly representative of the population. For example, if a random sample of 12 were taken from a population with an equal number of males and females, there would be approximately a 1 in 5 chance that 2/3 or more of the sample would be female. Such a sample would not be representative, although it would be random. In short, only with a large sample size will a random sample ensure an approximately representative sample.